our final lecturer, Danilo Prikashnikov from Kiel University in the UK. His mini course will be on low frequency vibrations of strongly homogeneous elastic structures. I hope it fits in well with the first three courses, right? It kind of concludes it and takes it to the realm of some applications to mechanics and wave propagation. Okay, and I'll pass it over to you then.
Okay, thank you very much, Kirill. Thank you very much for inviting me to take part in this splendid event. And this is a joint presentation together with Julius Koplanov and Ludmila Prikashnikova. I'm happy to see both of my co-authors attending. And indeed, we will be talking about the effect of high contrast on vibration, specifically in low frequency region of elastic structures. So I guess, well, knowing Kirill for some time, I may guess that probably my talk would be slightly less rigorous and slightly more applied here. Okay, so first of all, just to say a few words about Kiel University, where I'm coming from. So Kiel is somewhere here, as you can see on the UK map. So here is London, somewhere here is Liverpool, Manchester, Birmingham, and Kiel is somewhere there in between. It is known for the very beautiful campus. In fact, some time ago, it used to be, well, it was a manor, so some noble person lived there. So that's how it looks in the summer. In the winter, we sometimes have some snow. And it is also a very famous place for squirrels. So at least they said it was so in 2015. Okay, so now moving on to the outline of my lectures. So today we will certainly start from introducing the subject and speaking about various applications. Then we'll focus today on the one-dimensional problems for strongly homogeneous structures. So we will discuss vibrations of multi-component rods and multi-span beams. That's the plan. And then in the next lectures, we'll be looking at high dimensions, but still scalar problems within elasticity, looking at analysis of dispersion relation, the effect of high contrast, deriving the model equations of motion, and possibly also discussing the boundary conditions, the approximate boundary conditions, and generalization of the Saint-Venant's principle. And then we will also be talking about the effect on layered plates, and if we have time, we'll also speak about the effect of strongly homogeneities in case of surface wave propagation, so that'll be coated half space. So starting this topic, let me make a few preliminary remarks. So first of all, certainly a number of modern applications that we have today, they are dealing with quite a number of different material configurations. So the success of material science is quite substantial. So we could have structures which involve materials with quite different properties. And so this could be really strongly inhomogeneous. And of course, there is a lot of enthusiasm to study this, but so far, well, in case of real structures, it was mostly based on some experimental observations, but not that much on some justified models. So in particular, there is no consistent multi-parametric approach, because indeed there are quite a number of parameters involved, and often it is just one parameter, and that's all. Of course, I should mention that there is quite a lot of rigorous contributions on the high contrast periodic media. And I guess there'll be quite a lot of papers, so I don't think I should be mentioning them here, because I can just mention that, well, quite a lot of contributors to this event would definitely be involved with that. So people like Kirill, Sasha, Igor, Mikhail Cherdancev, and so on. So at the same time, when we talk about high contrast homogenization for this media, we usually have this periodic assumption, whereas in my talk, we are focusing on finite structures, so multi-component and finite structures. Okay, so let us start with discussing the applications. Well, one of these applications, one of the natural one, is certainly photovoltaic panels. And if we look at the number of papers that, well, in engineering journals, there's quite a lot of papers dedicated to them. And this is a classical example of a strongly inhomogeneous structure. It has a lot of layers. And also, as some authors point out, the difference, the ratio of, say, stiffness between the two components, well, the two extreme ones, say this ratio could be as small as 10 to the power minus 5, which is quite a lot. So this is a really strong inhomogeneous structure. And certainly, well, from our perspective as mathematicians, having such a small parameter at hand already suggests that it's a good object for investigation. So another example is a laminated glass. So that is also certainly a layered structure. It's a slightly different one. So typically there'll be 3 layers there. It would be the outer ones would be stiff and thick, relatively thick, and there will be a thin interlayer. To be fair, perhaps it's best to model it as a time-dependent material because it's usually a polymer, but so far we haven't yet done it because it just leads you to a number of unpleasant integral relations. So I guess we will still be doing it, but in future. So it's a future plan. And as for now, we were assuming that it's elastic. So some more examples, certainly classical sandwich structures when you have a thick and light core and covered with thin and hard skins. Yeah, that's, I mean, there are endless papers on that. Some variation of the same thing in applications to insulation, so getting some more layers involved, some potentially adhesive layers, and so on. So again, another applications of high contrast structures. Now, a relatively recent direction, but very, very actively developing, is the one associated with soft robotics. So sometimes, in the past, we were used to the fact that a robot is made of basically metal or steel, whatever. But nowadays, they're trying to make the properties much softer, so they're trying to borrow ideas from nature, and this is quite a popular source. Well, not the journal, of course. And also, once we started thinking about soft elements, soft robots, then hybrid constructions also come to mind. So there were these ideas of combining hard and soft components within robots, as you can see, for, well, almost 10 years now. So there were some examples from these papers, but also I found a recent one. So again, the same field is actively developing, and so in this paper they are trying to create a hybrid robot which is inspired by the tail of this monkey here, and certainly, as always, it would be high contrast scenario because we will have the hard skeletal element and relatively soft muscles there. Well, again, it's a big question about realistic modeling of this soft tissue. So you might need to look into soft materials and models for that. But at the same time, it's still a nice application. And as you can see, well, they're trying to create a similar device which would hopefully be as useful, maybe even more. So this is also nicely combined by biocomposites in general. So certainly there is a lot of interest in bioengineering. And if we look at any biological applications involving, say, teeth, bones, whatever, so they would often contain this soft part and hard inclusion. So again, this is another natural application. Okay, so I guess that is probably enough about applications, and let us go to more to the problem. So today we're talking about one-dimensional structures. So one of the first things that come to mind is this multi-component rod. So we have n components here. The hard components are shown as darker ones, so the softer will certainly be lighter ones. And we can easily have contrast in stiffness. So suppose, well, we can assume that, well, this ratio in the future problem that we'll be looking at the case of alternating stiffness. So there is also a possibility of contrast in density, of course. So that's another option. There is also a possibility of having contrast in length. So in fact, there are many, many ratios here and a lot of parameters in this problem. So since these problems are likely, since these parameters are likely to be small, it is very natural to use asymptotic methods. And so if we are looking at this thing vibrating, what does physical intuition tell us? It will tell us that the stronger components would perform almost rigid body motions at leading order, because, say, the softer parts would hardly affect really. And the weaker components, at the same time, will take all of the effect of deformations on themselves, so there'll be almost homogeneous deformations, well, at leading order. And this is certainly, we're not covering some rather special regimes of vibration, so it's about low frequency vibrations here. So that's a natural thing. So if you take a piece of steel and attach it to a sponge or something and then start vibrating this thing, you will see that indeed the steel virtually doesn't deform, doesn't change at all, whereas it's all been taken by the sponge. Right, so that's the general layout. Before that, let us start with something a little bit simpler. So I would say a few words about the two-component rod first. So before that, I would just mention briefly a paper by Ludmila with co-authors in 2016. In particular, they were mentioning there an application to this energy scavenging fabric devices. So if we look at it, well, there is this in small, how to say, some kind of a piece of fabric or some helical string probably, but really a nano scale, micro scale, yeah, so covered around that. And so when some vibrations happen, it does scavenge some energy. So in fact, why I wanted to show it here, just to show that this is indeed a similar layout to what I was going to talk about, namely a two-component rod. So if we start and look at this in detail, this is probably the simplest possible setup that we may have. And also, I was told by Kirill that there will be some students in the audience, so I thought it'd be nice to start with something relatively simple. So if we have a two-component rod, so we have a hard component here from L1 to L1 plus L2, and a soft component between 0 and L1. So well, the quantities, say E1 would be the Young's modulus of this weaker component, of the softer one, and the length L1 and density ρ1. And similarly, E2, L2, and ρ2 are the material and geometrical parameters of the hard component here. So we have these assumptions here. And again, so immediately we see that, well, in fact, we have three ratios, even in this simple case. So to get all three, possibilities of relation between all three is probably a bit too much for now. So we will just make our assumption. So we know that this is a softer component. So definitely the ratio of stiffnesses would be small. And we can also expect the ratio of densities to be small as well. And moreover, I think for the sake of simplicity, we would be assuming that they would be of the same order. So when we take E over ρ, that would be a quantity of order 1. Right, so if we start with the usual equation of motion for a rod, the classical 1D hyperbolic equation. For the purpose of our talk, we may easily make it even more simple because we are interested in time harmonic motion. But before that, we will also introduce dimensionless quantities. So we dimensionalize the horizontal variables, so scale it by L1. So the interface here is chi equals 1. We also introduce these two scaled frequencies, and C, well, as usual, C is the speed, the associated speed in the rod, the velocity. So if we assume in this harmonic time dependence, then the PD immediately becomes only differential equation, very easy to solve. And so now we need to discuss the conditions. So first, let us discuss the continuity conditions at the interface point here at chi equals 1. So we want the continuity of displacements and stresses. That's natural. And then if we start talking about boundary conditions, here there are 4 possibilities. So we can have either fixed free boundary conditions. So here this soft part, well, this is fixed here, and this condition here at the other point, at the other end, means that the hard component is has a free end. Yeah, so we can have an opposite scenario, a free fixed. We can have both ends fixed, and we can have both ends free. So 4 possibilities for the boundary conditions, but the continuity conditions will be always the same. And now let us start and look in detail at one of them and then comment on the others. So solving the equations of motion is a trivial thing to do. So naturally we'll have a linear combination of trigonometric functions, especially since we're also interested in vibrations. We know that we are expecting them. And so now if we focus on this free fixed case, so that would mean that from the boundary condition. So free fixed is actually must be fixed free. Yeah, I think this is case A. Just fixed free. Sorry, I changed it there, but I forgot to change it here. So what I mean is that this this weaker end is fixed, and the hard component there is free. Okay, so this is the case we are looking at. So if we start substituting into the boundary and continuity conditions, substituting u1 of 0 must be 0 immediately tells you from here that a1 must be 0. Now, if we put the derivative of u2 at phi equals 1 plus 1 over L over there. So we will get this, and these are the two continuity conditions. So we have, strictly speaking, 4 equations for our nodes, but of course the first one is trivial, so it simplifies, and you get a 3×3 determinant that gives you the frequency equation. So this is what we have from it in terms of trigonometric functions. We can certainly make it a little bit better if we divide by cosines and get to this scale parameters E and C. So E would be E1 over E2 and C will be C1 over C2, a ratio of speeds. So what we know that E is a ratio of Young's modulus, so that would be small. And we also know that the C, as I was saying, is a quantity of order 1. So we have a product of 2 terms equals something small. That's the frequency equation. And in what follows, we will be looking at several options. So we'll be looking at either global or local low frequency regime. So for now, let me introduce the global low frequency regime. So that means that both of these scaled frequencies are small. And indeed, if we look at this equation here, we can see that it is certainly possible that the product of 2 terms equals something small allows you to have both arguments of terms to be small. So this is not impossible. So yeah, just to confirm that is so GLF, global low frequency regime, is possible here. Okay, so that's the first type of boundary conditions. Now, if we start looking at the other cases, I don't think we need to look at them at that detail. So if there will be a need to do some exercises for students in the meantime, they could certainly try and derive these equations. So for the second case, for the free fixed case, so that would mean that the end of the softer component is free and the end of the hard component is fixed. So in this case, we will derive a very similar equation. The only difference is that now it's C over E, but not E over C like we had in first case. So now, since E is small, that means we have something large in the right-hand side. So that apparently doesn't allow you to have argument of terms being small. Yeah, clearly it's impossible. If we look at the both cases fixed, we can also derive this frequency equation. It would be something like that. And again, we can see that because of the fact that E is small, you can't really have a scenario that both of these arguments are small. And the same thing would happen for the free case. So actually, if we are looking at all of these 3 other types of boundary conditions, we cannot see that there is a possibility of global low frequency regime here. So the conclusion that we make from there is the one that we would naturally expect, that from physical observation, from physical intuition, that the global low frequency regime, so it's that both of these components, in a way, these trigonometric functions may be approximated by polynomials. That's the idea behind it when we're talking about the eigenforms. So it is possible when we have a Neumann type conditions for the hard components and Dirichlet type conditions for the soft components. So that was an example of just having 2 components, the simplest possible. So now let us move on and discuss some more options for the 3-component rod. In a way, we will be looking at probably slightly different. We will be looking at it slightly differently compared to the previous one. So we won't certainly consider all of these possible boundary conditions. We would know already what we want for this global low frequency. So we would know the configurations that we need. Okay, and we will also look not only at the global low frequency, but also at the local low frequency regimes here. So it relies on the material of this paper. So if we look at the at this structure. Now, the nice thing about it is that they are symmetric. So that means that if we were to look at the solutions for displacement, we can split the consideration into symmetric or antisymmetric motion. So we would know immediately either sine or cosine would be the behavior of the middle component. And so it will be only 3/3 determinant. Okay, so the equations of time harmonic motion are very similar to what we used to have before. And the boundary conditions now, if we are looking at this scenario here, when you have two hard components, the outer one, that would mean they are free. Yes?
Sorry, could you go back a few slides and show us where you introduced lambda 1 and lambda 2? Sorry to interrupt.
Yeah, sure, no problem. We introduced them for scaling, so to have it dimensionless. Yes, here it is. So it is frequency times length over the speed.
So okay. Right.
But you see, the thing is that they are sort of local frequencies for both components. So it does make sense.
So
because it might be the situation that, say, one of them is small and another could be order 1, depending on the scenario. So, but at the same time, they are both dimensionless, so it's useful to have them different in different components.
With what?
With each other. Because Ci and Ai are constant.
Yes, but you can make you have C1, C2, and 1 and 2. So the ratios between those are non-dimensional. So you have at least 2 parameters. You have 2 parameters. Yeah. So you can play with those to make lambda 1, lambda 2 have different orders. Okay, yeah, thank you. We are okay now. Yeah.
Yeah, okay, so we can move back. Yeah, so move forward, I mean, to this 3-component one. Yeah, we'll get there soon. Okay, yeah, so because we were already looking at the derivation for the 2-component in more detail, so here I'll probably derive this frequency equation in an easier fashion. So basically we are introducing similar scalings here. The structure is symmetric, so chi is x over L1, the same scaled frequencies lambda I, ratio of length, ratio of speeds, ratio of densities, and Young moduli. And finally enough, when we derive the frequency equation, we actually get the same thing as we had there for the 2-component, because basically it's the same, well, a very similar type of structure, yeah, because you have a hard component with a Neumann type condition and a soft one which is squeezed in between. So because you have an antisymmetric one, an antisymmetric motion, you must have 0 at the center. So really it's a very similar structure. No surprise that we get exactly the same frequency equation. And so now we will introduce the 2 options for low frequency regimes here. So we could have either global low frequency behavior that we have discussed already. So that's the case when both lambdas are small. That's one option. Another option is when we have local low frequency behavior. So only one of these lambdas is small and the other is not necessarily small. It could be order 1 or whatever. So let's focus. So these are the displacement that we can find, just the eigenform. So it's usual trigonometric function. So now let us have a look a bit more into these global and local regimes. So starting with global ones. So if we have this global low frequency behavior, it's very easy to derive an approximate frequency equation. So we just replace the tan functions by their arguments, and now that becomes absolutely trivial. So just the product of lambdas equals something small. And also we know that because of these lambdas were introduced in such a way that this is the same frequency omega but scaled differently, then obviously lambda 1 and lambda 2 are related. So you can express one through another, and so you can easily find these solutions, approximate solutions for lambda 1 and lambda 2 here. So they are really, really elementary. And now, if we know that we want this to be global low frequency, that means lambda 1 must be much less than 1 and lambda 2 also must be small. So that gives you that E should be much less than L from here, and from there L should be much less than 1 over rho. And that tells you that immediately these conditions for having this global low frequency regime means this double inequality on parameter. And this is a very nice condition because it is indeed very simple. So all you need to know is just tell the the lengths, the densities, and the stiffnesses. But as a result, you will see that if this condition holds, then we will have this global low frequency effect. So, and that would be particularly useful when we will move to talking about this vector problem in elasticity, about the three-layered plate, because in case of a three-layered plate, you can still find this three-component rod inside as a cross-section. We'll be looking at these fibers, so we will return back to this condition when we get there. Okay, so certainly in this case, if they are small, we can replace the trigonometric functions so by their approximation. So the argument is small there, and we have a polynomial eigenform. So certainly trigonometric functions of small arguments can be replaced by polynomials. And what we see here is the eigenform, the approximate one. And it does show, again, it has a very clear physical meaning. Because if you look at the profile of the structure here, so we have two hard components. We have their axisymmetric, so their antisymmetric motion. So it means it's just moving like that. So it's getting either symmetrically longer or shorter, so extends and contracts. So in this case, we can see that the hard component is moving as a whole, so it is a rigid body motion. So again, the same analogy with steel and soft sponge in between. So steel moves there without any trouble. And all the deformation gets onto this soft middle part, so it is a homogeneous deformation here. We can see it having a constant gradient. Yeah? And again, a constant for the other part. So that is the eigenform. Well, in fact, what we've done so far, we've just taken the exact solution and we have looked at the approximation and taken the leading node approximation for this trigonometric function. Of course, the same thing could be obtained by perturbation scheme. So if we tried, say, in more difficult scenarios when we wouldn't want to solve the equations exactly, we can certainly use the perturbation scheme. So what we can see from here, the displacement will be expanded as asymptotic series. As for this scaled frequencies, actually you can see they are sort of square root of omega. That's roughly the root. It would be seen that it is indeed the scaling that works there. And so in this case, what will happen, so for this structure, how it will work, we will take the leading order solution for the stiff components first. So that basically means solving a second order derivative equal to 0, yeah, because the inertial term will be effective at the next order. It will only be coming at the next order because of the small frequency. So therefore, at leading order, we will just have second order derivative equal to 0. So the solution is obviously a first order polynomial, and subject to Neumann type boundary condition, not surprising that we just have constants. So we will have constants there, and then we'll be relating these constants when we solve a similar second order derivative equal to 0 in between, and we'll be linking through these interfacial conditions here on the contact points, and we will get a linear function there. So certainly a perturbation approach is also possible, but here it is rather trivial. We will be showing it in slightly more detail in future problems, which require a bit more elaborate work. Yeah. Okay. So moving on now to some examples of local low frequency behavior. So suppose we want to consider local low frequency behavior of the inner component. So that means that the inner component will, well, lambda1 will be small. Yeah. So the inner component, the eigenform, will be approximated by a polynomial. So that's what it is. Whereas for the outer ones, they would be trigonometric functions. So there will be oscillations there. We won't be able to replace it by polynomials. And I guess this is certainly related to the works that were done in homogenization as well, probably in like 2000s, maybe 2008 or something. So if we now want to take the frequency equation and approximate, we can only replace one of the terms by the argument. And also because we know that lambda1 and lambda2 are related, it just gives an equation like that for lambda2 that we may look at. And generally speaking, it's a transcendental equation. We can't solve it exactly, well, analytically, but we can look at some special cases here. And this will be the displacement profile. So in the middle term, we will replace this by a polynomial, yeah, because it's lambda1 is small. But as for the outer ones, we are certainly having the trigonometric, some oscillations there. Okay, so now let us look at some particular cases for this equation. So first case is what happens, well, just remind you that the equation was tangent equals to that fraction. So what happens if your right-hand side is small? That means that the tan is small and you can have an easy approximate solution. We know that lambda2 is not 0, so that means it should be some zeros of tan, well, close to them. And this case may have a nice physical interpretation that would be associated with this sort of resonant vibration, well, vicinity of these resonant vibrations for the strong outer parts having free ends. And we can also derive conditions for the parameters when this thing happens. That was one possibility. Another possibility is when this right-hand side of the equation is actually large, then tan being large, we know the argument would be around these numbers, well, this pi over 2 plus pi n. And we can also derive roughly when it will happen. So the conditions for n, it will, if it is around these numbers, then we can hope for this type of solution. And this is already a difference in scenario. So that would correspond to antisymmetric motion, but for the scenario when you have a hard component in the middle and two soft one outside. So the soft one would have this fixed free resonances for the associated with these frequencies. And now let's look at some of the displacement profiles, so approximate ones. So for the first one, you can see something like that. So the middle part here has suffering the almost homogeneous deformation. That's again the approximation, and the outer parts they are the usual vibration. That's the first mode. So for n equals 2, you'll have more oscillations and so on. So here we are taking the scenario when the lengths are equal, just for the sake of simplistic illustration. Okay, some more profiles. So here we have another scenario. So this is already a stiffer part, as you can see from the parameters being taken. So actually that means that the inner part is 10 times stiffer than the two outer components. But still we can have a similar setup when this internal part is having this linear variation, and the outer parts are are just oscillating, right? So that's another possibility. Now let us look at this sort of opposite scenario. So now we can have a situation that, sorry, I think I meant something different here. Yeah, this should be lambda 2 and this should be lambda 1 now. I'm sorry, I'll correct it. Okay, so that would mean now that we are talking about lambda 1, and lambda 1 should be of order 1. Again, apologies, this 1 and 2 should be switching places. I just cut and paste there. But we can get similar to particular cases. So now the internal one will be sine, yeah, and so how will this equation be solved? In a very similar manner. There are two particular cases, and I think I can just show you the profiles. So you may have this vibrations inside now, and the polynomial dependence in the outer components, and the same thing just for the second mode here. So this is an example when the internal part is softer. So that's a possibility for the local low frequency. Well, I guess it's again a question how we can actually realize that, well, given a real structure, but the equations definitely tell us that these regimes are possible. Okay, and then the other possibility for the second case, we have even more interesting case when the outer ones are just constants because of this -1 to power n. There was cosine function there of n pi, basically that's the reason for that. And the internal one would be just oscillations. Okay, so these are the local low frequency behaviors for antisymmetric. So we were only looking at antisymmetric motion before. Now let me show you briefly the results of symmetric motion. So in case of symmetric motion, the frequency equation may be derived in a similar fashion. Just instead of tan, we will have cotan functions and similar displacement, but now there will be certainly even functions. And in terms of the global low frequency behavior, we can again replace the arguments, derived conditions, and again get this approximate polynomial eigenform, which will look differently now. So it must be symmetric. It has a constant variation associated with this hard inner component, and linear variations associated with almost homogeneous deformations of the softer parts. Right, so I hope that I was able to convince you that even a 3-component rod has a lot to look into. And of course, there were more things there. In principle, certainly you can make it inhomogeneous, and we were doing that in a paper. So we were looking at the case when the Young's modulus was a variable along the longitudinal coordinate. But I think now it's probably time for us to move on and see how we can generalize it to a multi-component rod. So we are taking it as a finite structure. So n is a finite number. The length is also finite. But at the same time, there could be, in principle, as many as possible here, but still not infinite. Okay, so clearly we would want here a perturbation approach because solving the problem exactly for arbitrary n would be difficult. And so for the sake of definiteness, let us again look at the scenario of alternating stiffnesses here. So so that would be E1, E2, and then E1 again, E2, and so on. So the lengths will be different, but their ratios would be some numbers, and we would assume they are of order 1. And we also want the ratio of densities being similar. So it would be again epsilon. So the ratio of the speeds would be of order 1. So that's the scenario that we want to look at. And if we start dimensionalizing the problem, then it does make sense to introduce local coordinates here for every component of the rod. And then the equations of motion would be something like that, where this capital omega is again dimensionless frequency. So I guess, well, it does have the same sense as lambda previously, of course. Yeah, it's just that now we have just C1 or C2, but Li, which is the length associated with every component here. Okay, so in terms of the boundary conditions, since we have this scenario when we have two hard components at the ends, and we are interested in the global low frequency regime, that means there should be Neumann conditions at the end. So we have free ends, and we also have continuity conditions. So we want to have continuous displacements and stresses. So that means that we have this epsilon factor here, and J is taking part 1 or -1, depending on which interface we are talking about, whether we transform from hard to soft or from soft to hard again. So, okay. Right, that's the formulation of the problem. And now we will start immediately with the asymptotic expansions. So expanding the displacements and the dimensionless frequencies for the global low frequency regime. So if we introduce these expansions into the equations of motion, just like I was telling you for a three component rod, we will have just second order derivative equal to 0, and there will be Neumann type conditions for all stiff components. So when it comes to the ends, it's natural. When it comes to the interfaces, it would follow from the fact that there was this epsilon to some power. So in case of this stiff component, it will just vanish. It will contribute only at the next order, at the corrector. Okay, so clearly solving this is not a problem. We can immediately deduce this is a constant. So that means that now, again, we are getting the same idea of rigid body motions appearing at leading order for stiff components, the thing that we have seen for a three-component rod previously. So it does work for multi-component as well. Now, next step, we are solving the problem for soft components. So again, we have second order derivative equal to 0 because the inertial terms only come at the next order. But now we have the continuity in displacements that are already two constants known from the stiffer components. So these are rigid body motion of the two neighboring stiff components. And so the solution therefore must be a linear function, just basically joining these two constants that we had previously. Okay, and so if we apply solvability to the next order equations for stiff components, we will end up in this homogeneous, well, in this algebraic system for frequencies for omega. So we will have the number of these equations will coincide exactly with the number of hard components here. So from 1, 3, 5, and so on up to n. And the solvability will definitely give us a polynomial equation. So the nice benefit of that is that the equation is not trigonometric but polynomial. And so the leading order eigenform would be piecewise linear. So as we have seen, there'll be constant solutions for the stiffer components. That would be the rigid body motions there. And also this may be certainly associated or related to a problem having masses and springs. Because if we want to go to the limit and take these hard components as just masses, and then these stiff or the softer components will be springs between them, then certainly you can consider such a problem for a spring mass system, and it is possible to show that this would actually coincide. In fact, we were showing this in that paper that I referred to previously. And so when we go to the next order, certainly we will it's possible to derive Ludmila did it in the paper, the correction for frequencies, and that would also imply polynomial correction to the eigenforms. So the ones that had constants will become parabolas, yeah. So that would just, I can show you an example how it would look like. So say if we take a 5-component rod and we have 3 stiff components, that means that we should have 3 equations in this system for omega squared. So after, because we know that all omega squares are related between each other, we can express them through a single one and result in a bicubic equation here. So it gives you a solution immediately. And that also leads us to some polynomial eigenforms. So for the case when we have a 0, that is corresponding to rigid body motion. So the whole structure moves as a whole. But then for the other 2 cases, we have something like that. So you can see for one of the roots, this is the leading order behavior. So that is just the, well, 3 constants and then the well, piecewise linear, and the same thing here, 3 constants connected with some straight lines. So when it comes to a refinement, it's shown here by dashed lines. So you can see there are polynomials of higher order, but well, just refining slightly, right? Okay, so I'm thinking, Kirill, when should we stop? Because it depends on the time. I'm certainly continuing further, but you can tell me.
I think you still have about 10 minutes.
Okay, that's fine. That's fine. So in this case, well, another development that was performed by colleagues in this area was trying to look at such structure here. So it was Julius did it together with Andrea Nobili from University of Modena and Reggio Emilia in Italy. So looking at this periodic waveguide, and it has some well, supports so of under some of these components. And again, there is contrast here in the parameters. So as a result, so when we look at such a periodically supported waveguide, so it could be either string or beam. They looked at both options in this paper. So the conclusions is that again, we can find this almost rigid body motion at leading order. However, due to the fact that this is a periodically supported waveguide, so there will be a non-zero cutoff frequency there, right? And also a few more reasons for that. So there happens to be a double cancellation there. So one cancellation happens over the supported region. So say here, you can see when the inertia force balances support reaction. So there is a proximity of global and internal cutoff. So you can look at the internal cutoff of the element of this, say, of part of this elementary cell here. And you can also look at the homogenized, the global cutoff. And because of the proximity between them, there is a cancellation there. Yeah. And also over the unsupported region, the inertial force will vanish due to high contrast, similarly to what we have seen before when we were looking, say, at the second order equation, and it was just the second or the derivative equal to 0. And the inertial term was only coming as a refinement at the next order. So these 2 cancellations happen there. And another interesting result there, well, when they apply this high frequency homogenization procedure, so they found that the homogenized equation for the string is quite an expected one. So that would be a equation of a string on the Winkler foundation, no surprise with that. But when they looked at the beam, so the 4th order equation there, then it would not be a Winkler equation, but it turned out to be a 2-parameter Pasternak foundation, so a more sophisticated model for foundation. Right. So now let us start talking. So I think that moves us forward to the next type of the structure that we can consider, low frequency vibrations of beams. So again, we can look at multi-span beams and have a high contrast scenario there. So now I'm talking about the two papers which were published by Julius and co-authors on the subject. And the difference now is that the equation will have fourth order derivative here. So in fact, certainly that would imply a lot more complicated physically compared to the rods. And so the reason for that is that, well, actually, when we talk about rigid body motion for a rod, it was only translational motion like that. But now, if we have a beam, it could have either translational motion or rotational motion like that. So that would mean that there'll certainly be a factorizations associated with that. Yeah. So now, although formally it is quite similar, the only difference is that we have a fourth order derivative here instead of second order. Right. So if we continue formulating this problem, so we have continuity conditions, which is certainly more of them now. So we have continuity of displacements, of normal angles of rotations, of moments, and of modified shear forces. And here again, we might have a similar small parameter ratio of Young's moduli. And that is just the intermediate value of length. So this sum of lengths that we have. Okay, so just like we had for the multi-component rod, we have this epsilon to power j, depending on whether we're moving from hard soft interface to soft hard one. It changes from 1 to -1. Okay, so in fact, here certainly there is a lot more boundary condition that we could consider, but because of the problem being more complicated, it's actually not that easy to derive the conditions on material parameters that would ensure global low frequency regime. So therefore, we are only considering here two standard types, two most popular types of boundary conditions. So one way is look at the free ends of this on this beam, and that would also remind us of having overrode a little bit, having the well, basically this is equivalent of a Neumann type in a way. Yeah, so when we have these free ends, but for the fourth order equation. So then another option is having simply supported ends. So this is also quite a popular condition from engineering perspective. So we'll be looking at both of these. Okay, so I've already said that, well, the range of boundary conditions is less clear. So it's to be honest, even for a particular boundary condition, when you take it and try to derive the conditions on material parameters allowing global low frequency behavior, it turns out to be quite messy and therefore not clear at all. So at the moment, this question is still open, so we don't really know the full range of possible boundary conditions that will be allowing this global low frequency for the beam, unlike the rod. Okay, so now if we perform the usual scaling, so introduce these local variables, and lambdas will be scaled frequencies again. But well, not, no, there's a square root. Yeah, due to the beam, it's a slightly different nature here. But it's still the idea is that lambda is related to sort of a scaled frequency. So then the ongoing element is described by that within these dimensionless quantities. Lambdas are related through this, and certainly we would like to operate in terms of lambda to the power 4. We have again the quantities of L, Ij being the ratio of lengths. And so P is a quantity here which allows us to write a general relation, but it is either 1, -1, or 0, depending on the numbers where we are in this structure. So we are assuming for the asymptotic process, we are assuming that the ratio of densities is the same as the ratio of stiffnesses. Otherwise, again, we will have to go into multi-parametric analysis, which will be a challenge. So I don't think it has been done yet for the beams. It still waits. Yeah, and the ratio of length must be of order 1. So then we are starting with asymptotic expansion. So we're expanding the displacements, and here we have to deal with lambda to power 4, and basically it's a similar assumption. Yeah, I guess there must be force here as well, probably, but never mind. Okay, and so when we get to the leading order problem, now it's the fourth order derivative equal to 0 instead of the second order for the rod, but today we have a lot more conditions here, and the solution for that would now be an arbitrary polynomial of the first order. And this is already, well, you can see again the rigid body concept working here. In case of the rod, a rigid body motion was corresponding to a constant. Here it is a linear one. So a constant term here, Bi, is associated with translation, and the linear term is corresponding to rotation. Okay, so I don't know, I don't want to probably take much time. So if you allow me to have slightly more minutes, I can finish with this derivation, or